Extraction and verification of turbulent structures. To extract the coherent structures in turbulence, the signals at the central area of turbulence should be selected. According to previous studies, the formation of the coherent structures in turbulence is formed in the area of zero. Advances in complex analysis and applications. This course is brought to you by Gilad James Mystery School. Learn more at giladjames.com. Introduction. The complex analysis development can establish three fundamental ways of modern research with the goal to solve certain conjectures and complete certain theories as the Lie groups representation theory, obtaining of a general cohomology for certain integral operators in the differential equations solution and extend these solutions to the meromorphic context. The three ways are defined for the relations between the complex analysis, with a cohomology with coefficients and holomorphic vector bundles, the hypercomplex analysis in a quaternionic algebra and the unitary representations in the Lie group theory. Likewise, some objects as modular forms can be the key for the multidisciplinary investigations in complex functions without the condition that Fc be holomorphic in the upper half plane. Then the modular forms are meromorphic functions. The before can be reflected in the satisfying of the certain functional equation Tfc equals xi, in which the conditions of the complex function Fc, respect to the transformation T, can be relaxed and the corresponding modular groups can be smaller groups. Such is the case, for example for the functional equation of the homographic transformation. The transcendence goes more beyond of the analyticity problems in complex analysis. The study of the complex Riemannian manifolds results relevant in algebraic geometry and strings theories, where complex Riemann surfaces as complex submanifolds can be useful in the determination of integration invariance. Also in the Frobenius distribution for the determination of integral submanifolds as cycles, whose values are cocycles in a spectrum of the category spec, of the category of the complex vector spaces Vec. The theory of Riemann surfaces can be applied to the space G, H*, to obtain further information about modular forms and functions. Likewise, the modular and cusp form spaces MKG, and SKG, for a group G, are of finite dimension, and their dimensions can be computed thanks to the Riemann-Roch theorem in terms of the geometry of the G- action on H. For example to the Lie group SL2Z, this finite dimension is computed as 1. In projective spaces, the functions are homogeneous polynomials. These algebro-geometric objects are the sections of a sheaf, one could also say a line bundle in this case. Precisely here arises the reinterpretation of the differential operators through the homogeneous polynomials of the corresponding lines bundle sections of their respective connections. Theta minus invariant on the complex interval minus 22 plus 01 I. It supports working with modular transformations and evaluating theta sums. With this construction of blocks, one can easily implement other modular forms such as Eisenstein series. http://frederiks.net/blog/2014/10/modular forms in arb/. However, there is other conjecture established years ago, which established the sentence. Conjecture 1.1. All complex function, analytic function, Fc, can be determined for hypercomplex functions. This could be obtained in a clear way, without pass for the holomorphicity. This represents all a joint research program between the hypercomplex analysis and the integral operators cohomology, and for it is established determine an integral operators theory that establish equivalences between cohomology classes on different complex base spaces and the cycles and cocycles of these under the corresponding integral operators. Likewise, can be obtained integral representations that are realizations of certain unitary representations of Lie groups such as UN, SU2, SUN, SU22, SUP, and UP, for the obtaining of the general solution of a partial differential equations in context of the quaternion algebra. And not only that, also are contemplated the equivalences of the corresponding cohomology classes obtained through the restricted objects to a space of certain dimension, for example, the hypercomplex analysis in R4C2, and in C4, is a quaternion analysis. Other example we can find in the integrals of the integral geometry of G2, 4C, through the space Pec, which establishes a twistor geometry. However, the isomorphism relations in homogeneous vector bundles are equivalent to the followed in cohomology developed in vector tomography. Likewise, the intertwining integral operators between cohomological classes of both contexts, respective cycles, result be cohomological classes in contexts of lines bundles, or equivalent cocycles. In this sense, a conjecture that can be proved is, the Penrose transform is a vector radon transform on homogeneous vector bundles sections in a Riemannian manifold, and considering the reconstruction of a Riemannian manifold through cycles, we can consider the following conjecture also. Conjecture 1.2. The twistor transform is the generalization of the radon transform on lines bundles, and the Penrose transform is a specialization of the twistor transform in S4. Of fact, the twistor transform can be determined for the Penrose transforms pair on G- orbits of projective spaces P- and P+. Then here arises the mentioned before in modular forms, the use of the lines bundles restricted to the polynomial rings corresponding to the subjacent operators on the complex vector spaces. In a more general sense, the vector bundles which refer us, are the seated in the homogeneous spaces GC/L, with homogeneous subspaces GC/Q, where is subjacent a holomorphic manifold with G- orbits, parabolic orbits, of GC/L, which have an induced Haar measure in each closed submanifold given for the flags of the corresponding holomorphic vector G- bundle. Then their orbital integrals are calculated on said orbits, obtaining invariants applicable to hold the homogeneous space in question, GC/L. This process, called of orbitalization of the homogeneous space GC/L, is based in major part in the inclusion of homogeneous spaces obtained for reduction of GC/L, through its holonomy. The spaces or cohomology groups of the complex corresponding of sheaves HSG/H nu n, result be fine representations of GC/L, through of the flags bundle corresponding to the complex holomorphic G- bundle in GC/L. The realizations of these unitary representations are the orbital integrals on the flags that are the K- orbits of the corresponding vector G- bundle. This is precisely used in representations of G-, a complex Lie group, constructed on spaces of holomorphic sections of vector bundles and generalizations as the studied for the modular forms. The problem that here arise, in the unitary representations, is the verifying of the Hermitian forms calculated through the diverse integral realizations with the corresponding representations, choosing the smooth and minimal globalizing, adequate. For it is used in a general version of the complex cohomology known as Macron- cohomology, called Serre generalization. However, this is not reduced to the obtaining of representations of complex groups. Also, the obtaining of an analytic function fc, of a space to other, is realized accord to the integral cohomology in -1 q Macron cohomology Hn-1, qcn/dv, where d is a linearly concave domain on C2. Likewise, for example, if we consider the space C2, the integral operator that obtains a harmonic function in R4, through calculated functions of C3, on lines S1, in C2, comes given 4. Which represents a transformation in cycles, lines, of a flag manifold F equals LLR4. Likewise, complex functions in certain complex manifolds can be obtained through complex or hypercomplex functions defined in complex subspaces, or submanifolds, which could be varieties in an algebraic context, for certain conditions of its cohomology. For example, in a complex sheaves cohomology, results interesting for problems of differential equations whose operators are germs of these sheaves. Other study is the singularities study through varieties, considering newly the complex varieties, in a pure algebraic treatment, or using the analyticity as a concept required for contour integrals to define a singularity as a pole of an analytic function. Likewise, in concrete, through an analytic function study, can be extended and generalized the Cauchy integral, as through integrals of contour can be generalized functional in a cohomology of contours, cohomological functional. The Moreras and Cauchy-Gorsatz theorems can be applied in a sense geometrical more general as cohomological functional of contours whose residue value can be modulo ls1 equals 2 pi. For example, two singularities or poles. This could represent the surface of the real part of the function gz equals z2 plus 2z plus 2. The moduli space of these points are less than 2 and thus lie inside one contour. Likewise, the contour integral can be split into two smaller integrals using the Cauchy-Gorsatz theorem, having finally the contour integral cgz dz equals c1 minus 1z minus z1 minus 1z minus z2 dz equals 0 minus 2 pi I minus 2 pi I equals minus 4 pi I. This is a good example of traditional cohomological functional element of HF pi minus L apostrophe omega r equals C. As a way to extend the meromorphic functions, the Nevanlina theory searches generalizations of extensions of analytic functions to algebroid functions, holomorphic curves, holomorphic maps between complex manifolds of arbitrary dimension, quasi-regular mappings and minimal surfaces. This is being applicable in moduli problems in Shimura varieties.